All right, let's talk a bit about scientific notation. Here's a couple problems where scientific notation comes up, and I just want to do these problems because I don't know, I think they're interesting. And these are things that come up in real life science and engineering applications all the time. And scientific notation is a way to describe these either really big or really small numbers. So first of all, the radius of the Earth is about 6 million meters. That's a distance from the center of the Earth to any point on the surface, more or less. And the Earth isn't a perfect sphere. It's a little bit wider around the equator by like a mile or something than it is at the poles. But anyways, it's about a sphere. Let's find the volume. We're going to use the formula V of r equals 4/3 times pi r cubed. That gives you the volume of a sphere. And we're just going to plug in the 6,371,000 meters into that. And so this is what we want to find is this result. We got to plug this into a calculator, unless you want to try to do that by hand. Be my guest. So here's a calculator. We're just going to do the fraction 4/3 times pi. Pi is, you get that by doing shift and then the caret symbol there, times 6,371,000, all to the power 3. And here's what your calculator tells you. It gives you 1.08, but that doesn't really mean 1.08 cubic meters, because that would be like not that big. It has this E with a 21 here. So what that E with the 21 really means is it means times 10 to the power 21. I'll move it over here so we can see it. Okay, so yeah, that's what this E means. It means times 10 to the power 21. And so when you have 1.0832 times 10 to the power 21, every time you multiply a number by 10, it basically moves the decimal place over one time. But we got to do that 21 times here. So really, this number would be, let's start, 10832. This right here is what you get after moving it over 4 times. So going 1, 2, 3, 4. And then we need to add zeros for the rest of them. So it's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 cubic meters. That is the radius of the Earth. You could write the answer like that if you have a lot of time on your hands and you really like writing zeros over and over again, but you're going to make a lot of mistakes if you try to do arithmetic with this because of all of the zeros that you have to keep track of. So instead of writing it that way, we're gonna keep it this way. This first way is what we call scientific notation, and just writing it out without a times 10 to a power is standard notation. And what makes it scientific notation is the fact that you've got the decimal point here and only one digit to the left of that. That's the way that makes it scientific notation. It's just having one digit to the left of the decimal place. Okay, now let's look at another example here. So the power from the signal from a cell phone tower varies inversely with the square of the distance from the tower. So let's say that P is the power and D is the distance. And we want to write an equation for the power in terms of the distance. But the fact that it gives you the fact that it varies inversely with the square of the distance from the tower, we can write an equation that is an inverse variation equation. It'll look like P equals K over D. But now we have to find out what K is that makes this work. And to find K, we're going to plug in the values that we know about. One value of D is 1 meter, and one value of P is 8 times 10 to the negative 7 watts. So let's plug those in here to get a value of K. K is unknown, but we do know 1 P and D here, so that's going to be K over 1. Oh dear, I made a horrible mistake. It varies inversely with the square of the distance. What I have is P just varying inversely with the distance. But the square of the distance would be D squared. That's really important. And that should be D squared here. It doesn't actually matter because 1 squared is 1. So this equation is really just saying 8 times 10 to the negative 7 equals K. So that's the value of K we can use, and we can say the equation now, it says find the equation for the power in terms of distance. That's going to be just P equals 8 times 10 to the negative 7 over D squared, because it varies with the square of the distance. Okay, so now we want to find the power at a distance of 1 kilometer. To do that, we need to know that 1 kilometer is 1,000 meters, also known, by the way, as 1 times 10 to the 3 meters, if you want to do it that way. And you can plug that in for the value of D here, because D needs to be in watts, because it's given that, or sorry, D needs to be in meters, because it's given that D is in meters. So we need to use one of these values with meters, not the 1 kilometer, because that's a different number. Okay, so we're going to have 8 times 10 to the negative 7 over D squared. I'll just write that as 10 to the power 3, and then that is squared. And we can plug this into a calculator too. And we plug this into a calculator, I'll have the numerator is 8 times 10 to the power negative 7. Whoops, except I need to get that parentheses out of the exponent, like so. Divided by the denominator is going to be 10 to the power 3. Whoops, I made the same mistake with that parentheses. Like so. Alright, so the result is 8 times 10 to the negative 13 is what that represents. And that means if we want to write that in just regular old standard notation, by the way, this is still a unit called, it's still in watts, because remember, P is in watts here, and the original P we plugged in was in watts too. So you could write this in standard notation. It would be 0.8, whoops, that's not standard notation. I'm going to take the 8 with a decimal place starting right here, and because it's times 10 to the negative 13, this is basically like 8 divided by 10 to the positive 13. So dividing by powers of 10 generally makes them smaller. So I'm going to take that decimal point here, which started out as right here, and we're going to move it 13 places over. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is where it should go. So we're going to have 0.0000000000008 watts. By the way, this is not usually the way you would write this number. You wouldn't usually measure this in watts. They have different units of measurements for things this small. 1 watt, by the way, I meant to say this the other way. 10 to the negative 12 watts is defined to be 1 picowatt. The prefix pico generally means 10 to the negative 12. And so we could also think of this as 0.8 picowatts. So you could write it either way, like that, or like that if you want it in standard notation, but that's a little bit unpleasant. Or how about just this way in scientific notation? Again, this is scientific notation because with a decimal place here, we only have 1 digit to the left of it. All right, now let's have you do a little exercise here. So let's pause it here and try it yourself. Here's my answers. I've got 1 digit to the left of the decimal place in each of these, 6 and the 1, so that's good. And then how did I figure out what the exponents would be, the negative 2 and the 3? Well, I knew this was going to be a negative 2 because I want to take the 6.3 and make it smaller to get that 0.63 there. So I would have to move this to the left, getting a smaller number than 6.3. And the decimal needs to move 2 places over to the left to equal the original number. So that's why that's a negative 2 here. And let's see, why is this a 3? Because, again, I want to multiply this 1.48 by something to make it equal to 1,480. And I need to move this over 3 times there to get that original thing, so that's why it's 10 to the power 3. Alright, now you notice we had no videos here about the rules of exponents. There's a whole lot of rules of exponents, things like a to the power m over a to the power n equals a to the m minus n. We're going to explore all of those in class, so that's why I don't have a video for it. And there's a really good activity in the book, so make sure you come to class on the day we do section 6.1 because we're going to review all of those rules. There's a bunch of them like that. And I will see you then.